So for our next talk, we have a very interesting talk titled Extending PyTorch for Custom Compiler Targets. And the presenter is Arash Taheri-Dezfouli, who is compiler engineer at Groq. Arash is a technical lead on Groq's compiler team, focusing on front-end integration with PyTorch, ONNX, JAX, and other ML/HPC frameworks. He received his master's and undergraduate degrees from the University of Toronto and has worked on compiler technologies for machine learning / AI workload for the last 7 years. You're welcome, Arash.
Right. Can everyone hear me if I speak like this? Yes. Awesome. Hi, everybody. My name is Arash, and I'm a technical lead on Groq's compiler team. Today, I'm going to be talking about extending PyTorch for custom compiler targets. So if you haven't heard about Groq, we made some news recently by being able to run inference on LLMs such as Llama 3 at incredibly fast speeds. This article actually came out back in April. Since then, we've continued to improve the inference speeds of these models. So this is a recording from our Groq chat from yesterday, and you can see we're already running at over 1,200 tokens per second, up from 800 back in April. And this video is actually not sped up. You can try this yourself by going to our chat at groq.com right now. So we achieve these speeds by having our own custom accelerator called the Language Processing Unit, or LPU for short. The LPU has a unique streaming hardware architecture, which is very different from CPUs and GPUs. This architecture, along with our proprietary networking, provides very low latency inference on LLMs. But the magic is not just in the hardware, but also the compiler that controls the hardware. The Groq compiler compiles machine learning and HPC programs from PyTorch, ONNX, and JAX down to the LPU. Groq compiler is an ahead-of-time compiler. So models from ML frameworks are transformed into tensor-based graphs to be consumed by the compiler. And finally, we rely on MLIR as a scaffolding and infrastructure of our compiler's dialects and passes. So let's go over the functionality of the compiler. The model is first imported, and memory layout and CPU vectorization are performed. Next, it is partitioned across multiple LPU chips using tensor and pipeline parallelism. Now, this is where the Groq compiler's method of compilation is different from other ML compilers. We don't have any kernels here at all. But instead, what we do is we map the program to the simple ISA of the chip, and then we schedule those instructions cycle by cycle. One of the key tenets of our compiler is to be as generic as possible. So what do we mean by this? We want to support a variety of models out of the box without hand-to manual work, such as writing model-specific optimizations. That being said, in practice, we find that while we can actually compile these models fine, our compiler doesn't always have all of the information needed to make the most performant decisions automatically. It sometimes requires a bit of manual intervention and some insertion of model-specific metadata in order to make the most performant and optimal decisions. Let's zoom in on the PyTorch pipeline to understand why our compiler doesn't have all the information. So the path from PyTorch to our Groq compiler has many intermediate steps. The Python code must first be traced into a graph. A series of optimizations and decompositions transform this graph, including things like constant propagation. This is the case whether we're talking about torch.compile with Torch 2.0 and FX graphs, or whether we're talking about TorchScript or even the ONNX export paths. The problem is that there's a large amount of information loss when PyTorch graphs are exported to these intermediate representations. We often lose the structure of the building blocks of the model as the model is unrolled. The precision of certain operations can change, and even the operations within the graph can be completely transformed to forms that don't fit well on our LPU. But it's not just information loss that's the problem. There's a disconnect between how these models are represented in PyTorch and the hardware that they run on. So anyone can spin up a model and make it run on hardware, but to achieve the highest possible performance, it helps when the algorithms and data science on the model side can actually express hardware-specific information to the compiler. Examples of hardware-specific information are custom hardware data precisions, and subsequently which parts of the model to run at these precisions, custom partitioning strategies and sharding strategies, that could be performant for a specific model, as well as representing the persistent KV cache buffers and their lifetimes. So with stock PyTorch, there's no easy way to express all this information and have it be compatible with PyTorch's various flows and their intermediate representations. Others have taken a more radical approach to this problem, where they've rewritten models in their own custom domain-specific language. So we see projects like TensorRT LLM, and these are really required because in order to achieve high performance inference on the hardware, PyTorch doesn't have mechanisms to express this sort of information. But as you can tell, rewriting a PyTorch graph in your own custom DSL requires a lot of manual handwritten work, and it's really not sustainable at the rate that models are coming out. So here at Groq, we want to avoid this DSL rewrite stage. So what if there was a better way to solve this problem? Compilers had this idea of encapsulation, where all state and information required for a compile should be captured into the intermediate representation itself. And then the PyTorch framework already provides formats for representing graphs. So why not take advantage and combine these ideas and encode information into the IR itself, the PyTorch IR, that is. That way we can actually validate the data and the metadata together, verify different information semantics, and make the IR the single source of truth. So what if we could associate metadata with the nodes and edges of a PyTorch graph itself? But instead of rewriting the model, what if our solution only adds information to the existing PyTorch graph? Okay, so that's a bit of a teaser. I know that everybody here is probably pretty familiar with PyTorch, but I just want to take a moment to review some of the building blocks of PyTorch because it'll be important later on. So the most fundamental building block in PyTorch is a torch.NN module. So you can define your class to inherit from an NN module. The constructor holds any state, and then the forward function defines the data flow. Modules can call other modules in their forward functions. As we see here, the child module is instantiated in this parent module, and then it's called during the forward function. So we want a mechanism to be able to add annotations to each module that we see here. There's a few reasons for this, but one that I specifically want to call out is the preservation of structure. So while PyTorch models are expressed in this hierarchy that you see here using NN modules, we lose the structure when the model is exported to PyTorch's intermediate representations. So we want a mechanism to be able to recover that structure. The next two fundamental building blocks of PyTorch are operators and tensors, which define the data flow of the model. So in this example here, X and Y are tensors, torch mapmul is an operation, and then it returns a tensor itself. So we want to be able to add annotations to both operations and tensors as well. Finally, the last fundamental building block of PyTorch are model parameters. So parameters are also tensors, but if they're assigned as module attributes, they become part of the module's parameter list. And during inference, parameters represent sort of the weights of the model. Annotations will help mark certain weights for transformations or extraction. Okay, so our solution is the PyTorch annotation library. PyTorch annotations is a library written by Groq compiler engineers that is meant to augment PyTorch. The library provides a set of APIs and decorators to be used in conjunction with the PyTorch building blocks. These annotations persist into any of PyTorch's intermediate representations and can successfully reach our compiler without being elided or transformed. This library is really meant to be used by compiler engineers in order to bridge the gap between models and hardware by providing hints to the compiler. The library provides annotations for each of PyTorch's building blocks that we just talked about, including module, operator, tensor, and parameter level annotations. So let's dive into each one of these. First, we begin with module annotations. Module annotations are done with a decorator that's placed on top of the module class definition. When the decorator evaluates, it will wrap the module and provide annotations on its edges. So this is an example of a module with 2 inputs and 2 outputs. When we annotate the module with the decorator, it will wrap the module and insert these pre and post forward hooks. Once a module is invoked, these hooks will actually insert the necessary annotations on all the inputs and outputs of the module. So we don't actually annotate the module itself, but we annotate the tensors at the boundaries of the module. Next, we have operator annotations. They're marked by the annotate op callable that wraps a torch operator. These annotations are very similar to module level annotations where they annotate the inputs and outputs of an operation with metadata. Next, we have tensor annotations. So similar to operator annotations, this wraps the incoming tensor and returns an annotated tensor itself. And then finally, we have parameter annotations. This annotation is slightly different than the other types. So it's actually done through a Python type hint. And the reason for this is because parameters can be used in multiple locations in the forward and backwards functions of modules, so it becomes cumbersome to annotate each use site. So instead, we annotate the declaration. So all of the previous annotations that I showed actually required the user to have access to the model source code in order to be able to add annotations. What if we don't own the model source code? So for example, what if we were getting the module from some sort of API such as Hugging Face? This is where module instance annotations come in. This is an API that allows module, operator, and parameter level annotations to be inserted on an instance of an NN module. So even if we don't have access to the model source code, you can still apply annotations, given that you have some knowledge of the model architecture, obviously. Okay, so now that we have an understanding of the PyTorch annotations library, let's explore a few use cases to illustrate why we might want to annotate graphs with metadata. Our first use case really is metaprogramming. So this is a method to extend PyTorch such that we can affect the way certain regions of the graph are executed on hardware. This can include support for custom data types that are not natively supported by PyTorch, custom sharding and partitioning strategies, and so on. Second, we have capturing program structure. So as I mentioned earlier, PyTorch graphs in Python have this hierarchical structure to them expressed through NN modules. The structure is often lost when the model is exported to any intermediate representation. If we can annotate the boundaries of this structure, then the compiler can actually recover them. And this can lead to things like code reuse, which helps lower both compile time and memory usage. Finally, we have symbolic constant compilation. So LLMs and their weights are huge, often needing large amounts of memory to be able to export and compile. Our compiler is actually capable of compiling models without weights and only injecting them at the very end of compilation. However, we can't just strip all of the weights from a model blindly because certain constants are critical for compilation. So with annotations, we can mark exactly which constants are to be extracted and perform the bookkeeping required to insert them back into the program post-compilation. Okay, so this is a simple example of metaprogramming showcasing how we can map hardware-specific data types to certain regions of PyTorch. So I'll walk you over this code. We have a simple module with two tensors, x and y, and we perform a matrix multiplication on those two tensors. There's a module level precision annotation, which tells the compiler that the inputs x and y and the result are expected to have float 16 data type. Then there's a tensor level annotation, which lets the compiler know to cast y to the float 8 data type. So the mapmul here is performed with the first input in float 16 and the second input in float 8. This would actually be illegal with PyTorch's regular operators, so the PyTorch kernels would actually complain about the data mismatch. But this is completely legal on our Groq's LPU, and it actually leads to huge performance boosts. So with annotations, you can actually see we are able to express such graphs to our compiler while still staying in PyTorch. So if this sort of metaprogramming appears strange to you, an analogy that might help is the comparison to OpenMP style programming in C++. OpenMP directives provide hints to the C++ compiler to enable loop and task-based parallelism. Here, annotations provide hints to our compiler to perform precision optimizations. Okay, so if we take a look at exactly what the precision annotation looks like. So any payload of annotations is designed to be very generic. It is made up of a simple key-value pair, where the key is a unique string for that annotation and the value is any serializable format. So for precision annotation specifically, the key is just the word precision, while the value is a Python dictionary containing the string representation of the requested data type. This dictionary actually gets serialized into a JSON string when it's inserted into IR, and I'll show that in a few slides. Okay, now let's explore what's happening under the hood. For any annotations library to work, we need 3 requirements to be met. First, we need a way to add metadata to each of PyTorch's building blocks and differentiate between each type of building block annotation. Next, we need to ensure metadata is retained during the various export pipelines. So this includes TorchFX, Dynamo, torch.export, TorchScript, ONNX, etc. And finally, we need to support any arbitrary metadata payload that we want to add on the annotation. So if we go back to the same diagram we had before, showing a module with 2 inputs and 2 outputs, the way that we actually capture metadata on the inputs and outputs is by inserting a custom operation called annotate module on each edge going into and out of the module. After the graph is exported, the compiler can inspect the IR to find the set of custom operations that represent a unique invocation of a module. So let's look at how we define these custom annotation operations. PyTorch has some very simple Python APIs that allow you to define an operation namespace and register any custom operation. So here we're showing the interface for the annotate module custom operation. It takes as input the tensor that is being annotated, followed by the serialized annotation string, which represents any of the actual metadata. It takes in a unique group ID. And finally, it takes in an argument indicating whether this is an input or output edge. And finally, it returns the annotated tensor. The actual implementation of the custom operation is a simple no-op, so the actual data flow of the graph is not affected. The advantage of using custom ops is that they're immutable in PyTorch's export and optimization flows. This way, we can actually store the metadata within the custom ops themselves instead of on core PyTorch building blocks, which may be mutated during the export process. To insert these custom ops on modules, the annotate module decorator we previously showed registers these pre and post forward hooks. This is what the module pre-forward hook looks like. The inputs to the forward function are first passed to this hook. Then annotate module custom ops with the respective metadata are inserted for each input. And finally, the annotated tensors are returned, which then will be fed into the actual forward function. The post-forward hook looks very similar. The outputs of the forward function are passed as arguments to this hook. They're wrapped in annotate module custom operations with terminal being set to true. And then finally, these annotations are returned to the caller. So these pre and post forward hooks allow us to insert annotations without needing to modify the module itself. And the best part is these hooks are fully compatible with all of PyTorch's export flows. So operator annotations are very similar in that they annotate the inputs and outputs of an operator. This is done by inserting an annotate op custom op. There's obviously no forward hooks here. Instead, our actual callable receives the input tensors, and it can just annotate them and then call the operation and then annotate the results. Tensor level annotations are exactly the same using an annotate tensor custom op. And finally, parameter annotations are a bit more involved. So they are annotated using an annotate parameter, but if you notice, they're only annotated once. And basically, we only insert it once and replace all uses of it through the graph. So if you recall, we expressed this annotation via Pythonic type hint. What I didn't mention earlier is that it actually has to be used in conjunction with the annotate module decorator here. When the decorator is evaluated, it will check the types of any parameters on the module. Because a parameter can have multiple uses, it's actually cumbersome to go through each use site and update them. So PyTorch actually provides a mechanism for us to do this very simply. So we can actually use fx to achieve this. So fx is not just the intermediate representation, but also provides infrastructure to rewrite any part of the module. So in this code snippet, what we do is we first trace the graph, trace the module to produce an fx graph. We then traverse the nodes and look for any constants within the graph. We check whether the names of the types of those constants match our type hint. And then finally, we replace all uses of the parameter with the annotate parameter custom op. The best part is that this whole process is compatible with any of PyTorch's export flows, even including legacy TorchScript. All right, so let's look at the backend of this pipeline now, where PyTorch's intermediate representations, such as fx, feed into our Groq compiler. So if we go back to our previous module, where we were annotating this mapmul to express custom hardware data types. So as a refresher, the forward function takes in two inputs, x and y. Y is annotated to be float 8, while everything else is annotated to be float 16. This is what the fx graph looks like when we export that PyTorch module. So it's a bit of an eyesore, but I'll walk you through it. So it begins with two placeholder nodes right here, which denote the x and y arguments to the module. Every other line here are the operations within the graph. So every call function is basically a call to a torch operator. The arguments of the operators are within these curly brackets or round brackets here. And then finally, the return statement at the end returns the result of the module. So we can see in this IR that there's 3 instances of the annotate module op. The first 2 denotes the inputs of the torch module, while the last one denotes the output. You can see that these operations clearly define the start and end boundaries of the module given in the unrolled IR. So if we pass such an IR to our compiler can actually inspect this IR, do a simple traversal, and extract the module out, regaining the original structure of the model. We also have the annotate tensor custom op, shown in green here. And finally, each annotation op has its encoded metadata shown in the purple box. So you can see this is the serialized Python dictionary I was talking about earlier. Basically, the module level annotations have a float 16 data type, and the tensor level annotation has a float 8 data type. Because this metadata is embedded in the IR in custom operations, it doesn't get mutated, elided, or transformed. It's important to note it's really up to the compiler to interpret the order at which to apply these annotations. Our compiler applies annotations in a top-down manner, meaning the module level annotations are resolved first before the tensor level annotations. And if we're speaking about precision, the Groq compiler actually has an automatic mixed precision pass that inspects the IR and marks precision decisions to optimize for accuracy and latency. So this pass actually gets things right 95% of the time. And for the 5% of times where it's too conservative or too aggressive, this is where annotations can come in and help. Okay, so I'm just wrapping up here. Annotations allow you to insert hardware-specific information and model-specific information into PyTorch graphs to get the best possible performance. They decrease the time required to get to a performance solution without having to rewrite the model in a custom DSL. All of this is possible because PyTorch is far more than an eager execution engine. It has a well-defined intermediate representation with utilities to modify the IR for your compiler. Okay, so in the future, we plan to extend the usage of annotations to enable other flows in our compiler. We plan on modeling device and host interactions and their interplay. We plan on using annotations to express distributed programming ideas. And finally, we plan on using the structure captured by these annotations to make smarter and more efficient decisions in the compiler. I want to give a big shout out to Zachary Setnick on my team. Unfortunately, he couldn't be here today, but this is his project, and a lot of the innovations that you see are actually as a result of him. So we plan on writing a blog about this project, so be sure to check out Groq's blog page. Feel free to reach out to me on LinkedIn if you have any questions. And finally, we are hiring. So if you found this talk interesting, please check out our careers page. And last, if you want to experience the speed of Groq's technology, check out our Groq chat. And if you want to build applications using fast LLMs, check out our Groq cloud to get API access. Thank you very much, everyone.
Hey, thank you very much for the presentation. First of all, the annotation library and the compiler is available to test out right now?
No, unfortunately, we haven't made it available yet. It's in the works.
Okay.
Yeah, we have to go through the process and see if we can actually open source it. Our compiler comes with our Groq SDK. So there's a whole process you have to go to get access to that.
Got it. Also, like, have you observed any model performance decrease by optimizing the latency or speed using the annotation? Like, I mean, the accuracy performance. So.
Yeah, that's a really good question. That's why the point at the end I was talking about, we do have an automatic mixed precision pass in our compiler that will inspect the IR and try to make an optimization for best accuracy and best latency. But sometimes it can be a little too aggressive or it can be too conservative, and it really is model specific. That's sort of where annotations come in, and we can actually just go in and add an annotation on the graph, and that'll sort of like fix that.
Got it. Thank you very much.
No problem.
Hello. So one of the things with adding all the annotations and everything, that is a bit of a manual task, I guess, for things. Meta recently came out with a paper called Foundation Models for Compiler Optimization, that is like doing a similar, well, training a language model to output intermediate representation and assembly code. And the end goal of this is sort of to have language models be able to find optimizations in that the compilers themselves haven't. Is Groq doing anything around using language models to be able to optimize the compiler itself, as opposed to the only compiler optimizations being the ones that humans have sort of come up with?
Yeah, that's a great question. I actually did read that paper as well. It is something that we're looking into. I don't have any data to share yet, but yeah, it's a very interesting area. I think it could really help, and absolutely, it's something that we're absolutely looking into.
Cool.
Hi there. I guess I have two questions. First, I was just wondering what the instruction set is for the Groq's chip, and second, like in your opinion, like what's the MVP here? Like, is it the compiler or is it like the chip itself? And I guess like I'm trying to understand like why is it that the chip is more performant than like just like a regular GPU?
Yeah, absolutely. So I could give a whole talk on this. Let me just go back to the very beginning. Okay, so our chip is actually quite simple. There is no multi-threading. There's no memory hierarchy. It's very much like a data flow and streaming sort of architecture. So the ISA of the chip, you can kind of see it here, but you have sort of vector ALU units in the middle. You have memory on each side, and then you have data switching, and then at the ends you have matrix multiplication. And then really at the boundaries you have I/O, where we can do our proprietary networking or talk to host memory. So the chip is actually very, very simple. It's this simplicity that really allows us to achieve performance. There's no context switching, your threads don't have to sleep. It all works as like, you can connect these chips up to other chips and it all works as one gigantic chip. And the beauty of the chip, again, I didn't mention this in my talk because I can talk about it for hours. Everything running on the chip is deterministic. It means our programs, we know cycle by cycle where any data is. There's no arbiters, there's no knocks, there's nothing like that. And so the compiler actually can compile cycle by cycle instructions to be running on the chip. And when we have that sort of availability, we can optimize the utilization of our chips such that we take advantage of all functional units. And you can even do cool things such as power profiling. If you know exactly how much power a model will take at compile time, you could do optimizations where you spread out the compute so you use a lower power profile, or vice versa, so you can get better power profile. So I would say it's sort of the simplicity and determinism of the chip which makes the compiler pretty powerful and do things that other compilers can't.
Thank you very much. Thank you. Just quick, yeah, you talked about, I think, and I see that right there, like custom partitioning strategies or sharding. Could you just explain quickly, like what, for example?
Yeah, so I'm not a sharding and partitioning expert at all, but basically our chips, so we use a multitude of chips to run these LLMs, right? They're all connected through our proprietary chip-to-chip connections. So these models don't all fit into the SRAM of our chip. Instead, we have to partition the models using both sort of model parallelism and tensor level parallelism. So we have analyses in the compiler that will essentially understand the hardware that you're running on and shard your model across all of these chips. And there's many different mechanisms that we use for doing that. Again, I'm not an expert, so I can't. So one chip is a single core. That's how we treat it. It's like a single core. And when you connect a bunch of chips together, it's still a single core. That's the beauty of it. Okay. All right. Thank you very much, everyone. Appreciate it.